and together we competed in the Stockholm Junior Water Prize competition. Now this is a science fair whose projects are purely based on solving water-related issues. So for our project, we wanted to tackle desalinating ocean water in an efficient way.
So some of the facts. 71% of the Earth's surface is covered in water, but only about 3% of that water is potable.
So the problem that we wanted to solve was the fact that people around the world are dying of dehydration and waterborne illnesses. Now we wanted to solve this problem by using the world's largest water resources, the ocean, and use it to supply these people with water. However, to do that, we need to take the salt out of the water. And there are modern options such as reverse osmosis. How many of us are familiar with reverse osmosis or have worked with reverse osmosis before? So quite a few of us. How about electrodialysis? Not so many. Or even distillation. Now, you are all familiar with the fact that these are large centralized systems and they are energy inefficient. So we wanted to come up with a system that was both energy efficient and decentralized. So to do this, we turned to CDI, or capacitive deionization. Now this is a process that uses capacitors to deionize an electrolyte. So how this process works is two oppositely charged electrodes face each other. Now when we charge the electrode, the ions are then attracted to the electrode and are held there until we discharge them. Now upon the discharge, the ions are released and we can then flush the ions from our system. And then we continue this charge and discharge until we have a desalinated or deionized solution. Now, another notable thing about capacitive deionization is the fact that upon the discharge of this electrode, it releases energy, and we can recapture that energy and use it to power the next cycle. Now, this is huge because it lowers our energy usage, and we are therefore more energy efficient.
So for our electrode material, we chose graphene. It's a revolutionary material made entirely out of hexagonal carbon rings. So some things that make graphene such an amazing material and so applicable to our process is that it has a huge surface area. 1 gram of the stuff has a surface area of about 2.5 tennis courts, just absolutely massive. And another thing is that when a current is passed through it, electrons travel ballistically, which means they travel almost without mass. And what this means for us is that we can charge and discharge our process extremely fast. So some current testing for graphene. Graphene is being tested in the medical field to enhance PCR, which basically turns a little DNA into a whole lot of DNA. It's being used in antibacterial bandages and even in gene delivery and make little packets out of this stuff. And it's being used in the medical field for anything from supercapacitors to transparent conducting electrodes for solar cells to collect the current off these cells.
So the reason that we use CDI with graphene electrodes is for multiple reasons. To start, it has a high surface area, which means that we can hold a lot of ions within its surface per cycle, making us much more productive. And in addition, it has a high conductivity, which means it's more energy efficient. And as Vernon said, the ions travel ballistically across it, so we're even more productive. This lowers our energy, or this lowers our costs and increases our energy efficiency. So for our experiment, we wanted to prove that capacitive deionization with graphene electrodes was a viable technology to desalinate and deionize water. So to do this, we used simple household items like DVDs, a DVD light scribe burner, and a computer to come up with a testing platform to test our project.
So, to make the graphene, we started out with graphite oxide because it's much easier for us to start this way and then to make it into graphene. So what we did is we took graphite oxide, we got it in a powder, mixed it in water, and then distributed that water onto our CD and let it dry for about 48 hours. Once it had dried, it was this golden brown color, as you can see on the screens. And then from there, we put it in our DVD light scribe burner. We used a simple cover art program just to burn the entire surface of the disc, and once that was complete, we pulled our discs out, and as you can see, there's a massive color change from our graphite oxide into our laser-scribed graphene. What had happened while it had been laser-scribed, as you can see here in this picture from Kaner Labs, is the graphite oxide, or GO as we like to call it, was then transformed into LSGU, laser-scribed graphene, by the infrared laser. And as you can see, it has been massively just blown apart by this laser. And the little leaflets that you can see, that's actually where the ions fit into it and then are held there until we release them. So our final DVDs, these actually were our final DVDs that we used in our process to make an interface with the graphene. We painted silver around the edge, and then to that we attached wires. As you can see on some of these DVDs, there are holes drilled through them, and that's to allow radial flow through our reactor, which Emily will talk about right now.
So here's a diagram of our final testing platform, and as you can see, contaminated water goes in through the top, and the water travels radially across the stacked discs that face each other and act as the electrodes. And as this is happening, the water is traveling radially across it so that it comes in contact with as much of the graphene as possible so we can get out as much ions as we possibly can. And then out comes deionized water. So here's just what we use to get our information from our testing platform into our computer. It's just a 13-bit analog to digital recorder.
So our raw data, before we did anything with it, we just graphed the points we got, and as you can see here, we got a galvanostatic charge and discharge. This is basically what you'd find if you did any research on a reactor, or on a capacitor. And when we're charging, we're actually removing ions from solution and holding them on our electrodes, and then when we're discharging, we're releasing those ions back into solution. And the amazing part about our process is that when we are discharging, we're actually we're producing electricity that we can later store and then reuse on later cycles to make our process even more energy efficient. So for our data reduction, we used math. Our conversion was volts times current times time, which were the 3 points that we measured, and this got us our energy required to deionize water. There it goes. From this, we determined the kilowatt hours per meter cubed required to deionize a sample of water. And then we put this into a Monte Carlo analysis, which is a statistical analysis which ran our numbers about 10,000 times and determined the statistical probability that our process would scale properly.
So when we put 35,000 parts per million salt concentration into the top of our reactor, or that equal to seawater, we got this graph. And as you can see, it's kilowatt hours per meter cubed across by the various technologies to desalinate water. And as you can see, reverse osmosis and distillation are extremely energy efficient in comparison to us. And we actually use a lot of energy in comparison, and we did not compete with them at all. However, when it comes to other samples of water, we showed high promise.
So, next we move to 4,000 parts per million. This is the really exciting part. We actually proved to be as energy efficient, a little bit less, we used a little bit less energy per kilowatt hour per meter cubed than modern methods of reverse osmosis, distillation, and electrodialysis. And this is all possible thanks to our energy recapture system. And next we move to 2,000 parts per million, which you find in an ocean delta, or maybe a contaminated well, or even maybe frack water, because that's a major problem in the world today. And we used less than half the amount of energy of these other modern methods, as shown here.
So, a summary of our results showed that we worked best with brackish waters, but when it came to salt water, there were just too many ions for us to be efficient at this time. However, upon scale up, we believe that we can become more efficient and even competitive with the reverse osmosis and distillation if we use scale-up systems such as feedback systems upon scale-up, and then the energy recapturing.
So some other applications. Since our process is so versatile, we can pull almost any ion out of solution. Some of these include nitrates. How many of you have problems with nitrates? Yeah. And then chlorides and sulfates, which are in hard water. And another problem that's a major problem in Japan right now is cesium-134 and 137. This is a radioactive ion that has contaminated hundreds of thousands of foot acres in Japan after that nuclear disaster in Fukushima. Another is chromium-6. This is a major problem here in California, as you can see in the lower picture. How many of you have problems with chromium-6? Yeah, it's a major carcinogen, and we believe that we are able to remove this ion efficiently, which has proven to be a problem in the past. And then lastly, perchlorate. They come out of rocket fuel and basically anything that goes boom. It is a major problem throughout the world today.
So, in conclusion, we find capacitive deionization with graphene electrodes to be a viable technology for desalinating and deionizing water. And we find that in the future, we may even be able to use renewable energy sources to power our system.
So what's next? Next, to scale our results, we need a little bit of time and a little bit of funding. And right now, we don't really have either of those because we're high school students. We do, however, have several ideas of how to scale our results, and all of these include finding a new substrate for graphene. We believe this could be a major technological and scientific breakthrough, because at this point there really isn't an efficient or cheap way to make graphene in the scale that we would need it for our project. Once again, I'm Vernon Wetzell, this is Emily Bettencourt, and thank you so much for your time.
So, by the way, their parents and grandparents are here as well, so let's give them a hand clap. Some of them are back there, some of them over here. And here's my question. How old are you? 17, and how old are you? 16. Wow. Innovative, right? And if George was here, I bet he'd be talking to these two people, right? Thank you two very much. We appreciate it. So talk about innovation. Look what's coming up behind you. So any GMs in the room that are looking to finance something innovative? There you go. Locally, just talk to Vernon and Emily. So we're going to move right on into our next presenter.